The rectangle below is built with algebra tiles. Find the area of this rectangle as both the sum of its parts and as the product of its dimensions. So I want to come back over, just step over to the side here and kind of review this a little bit. So let's consider the following. Let's say that I have a triangle, a rectangle rather, that's 4 units across the top. And we're going to say that it's 1, 2, 3 units on the one side. So across the top, it's 4 wide and it's 3 tall. So each one of these pieces, right, this is a 1, 1, 1, 1. Down here, this is a 1, 1, and 1. That's how I get the 4 and 3. Each one of these pieces has an area of 1 unit. So that's 1 square unit, 1 square unit. These all have an area of 1 square unit. Now, I can write this area as 2 ways. One of them I can write as the product of its dimensions, right? 4 times 3 is the area. I can also write the area as the sum of its parts. Well, the parts here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 12 of them, right? So this is what I'm talking about. I want the area expressed in 2 ways. One of them is the product of its dimensions, 4 times 3, and the other one is written as the sum of all of its parts. Here all the parts are just ones, so I can just combine them all together. It's 12 of those ones. So let's come back to our problem now. So again, this is built with algebra tiles, and we know something about the dimensions of algebra tiles. So let's go ahead and fill in what actually we do know about the dimensions. Again, this particular square has dimensions x by x. So when I multiply x times x, I do get the area of x squared. That's the area of this piece. But across the top, its dimension is that's an x long, this is x long, this is x long, and each of these tiles are 1 unit long, a 1 and a 1. Now going down the other side, this dimension is x units long, and this dimension is 1 unit long. So if I look at this now, the dimensions of this rectangle, right? If I go across the top, there are 3 x's and 2 1's. So we would customarily write that down as 3x and 2 1's. So one of my dimensions is 3 x's and 2 1's. The other dimension is a single x and a 1. So if you look at it, I've got the product of 3 x's plus 2, and I'm multiplying that by x plus 1. That's part of my answer. That's the area written as the product of its dimensions. I'm going to go ahead and put this on the second line, although probably I should be putting this on the first, but 3x plus 2 times x plus 1. The other way I can get the area is I could write it down as the product of its dimension, or the sum of its parts, right? That's the product of the dimensions. Let's write it down as the sum of its parts. Well, if you look at it, I've got 1, 2, 3 x squared parts. So this area contains 3 x squared tiles. It contains 1, 2, 3, 4, 5 x tiles. So I'll write plus 5 x tiles. And it also contains 2 1-unit tiles, so plus 2. So this is the area of this rectangle as the sum of its distinct parts. And that area is 3x squared plus 5x and then plus a 2. And of course there's a relationship between these two. They're equal to each other. The reason why they're equal is they're both the dimension, they're both the area of this rectangle. One is the product of the dimensions and one is the sum of its parts. Just like over here, when I look at this, 4 times 3 is the same thing as 12, right? The area of this rectangle is 4 times 3. The area of this rectangle is 12. However, this is kind of important to focus on because this is helping us understand a little bit better how it is that we multiply binomials, and there's a lot to be learned and a lot to be observed there. Let's see, question 13.